All right, let's go ahead and start intermediate value theorem for today. It's on page 15 in your notebook, so go ahead and take those out and take a look at these. We're going to go ahead and skip the goal problem for today. Let's just go ahead and do bullet point number 1. Consider a plane that takes off and climbs from 0 to 10,000 meters in 20 minutes. Was the plane's altitude ever 8,623 meters during the 20 minutes? How did you know? And if we just step back and think about this non-mathematically and just logically, I think that we can say that if I start at 0 meters, go to 10,000 meters over 20 minutes, and during that 20-minute time frame, do I ever hit 8,623 meters? The answer to our question is absolutely 100% yes. We should hit 8,623 meters if I'm going from 0 to 10,000. So let's go ahead and draw this out just to be able to give ourselves an illustration of why this will actually work. I'm going to draw a plane by writing the word plane. And my plane in my trip is going to take off. And at some point along the way, hit a little turbulence, maybe drop down in some altitude. And then out here is where I'm going to say 20 minutes and 10,000 meters occur. So there's my plane. There's the flight path. Now, let's math this up a little bit. Let's go ahead and graph or turn this flight of a plane into a graph. So I have an input or an independent variable of 20 minutes. So I'm going to start my x and y axis here where my plane started. Drawing a little x-axis. And this is what? Minutes for x. And when I get to the end over here, that's got to be 20 minutes. My output is going to be, we're going to call that f of x. And for f of x, we get up to, 10,000 here? And this is in meters. All right, so 20 minutes from 0 starts at 0 minutes, 0 meters. At 20 minutes, we end up at 10,000. My plane hit a little bit of turbulence, so I get a little bit of maybe a max and a min in my graph here. And if I'm going to illustrate this graphically, I can hit 8,623. Let's put 8,623 about here. And if I draw a little dashed line across, we can see that I hit 8,623 meters. Now, we're starting to go from a plane taking off, and we're trying to build a mathematical situation that's going to allow us to show or prove that 8,623 is achieved. So now let's go through and write a rule for the plane's trip explaining why it had to reach a height of 8,623 meters. This is our proof here, and we're going to do this mathematically. Okay, and I'm going to start with, I think, the part that logically we go to first. I think at least I'll speak for myself. When I think about this, if I start at 0 meters and I end at 10,000 meters, I always have to hit 8,623 meters. And that's true, right? And we can write that. So down here I'm going to write, start at 0 meters, end at 10,000 meters, and 8,623 is bigger than 0 or less than 10,000. So this is my initial output, let's just say. And this one is my ending output. Now, the other thing that I need to take into consideration is the input values, right? If I'm asked if I go from 0 to 10,000 meters over 20 minutes, and they ask me, was the plane's altitude ever 8,623 minutes after 40 minutes, let's say, well, that 40 minutes is outside of the information that I know. So it would be very hard for me to tell if I actually reached that 8,623 minutes. So I feel like I'm going to also have to say something about my interval from 0 to 20. So I'm going to say over, and I'll write this one in interval notation just to show you that we can do that too. Over 0 to 20 minutes, right? We're given an input, a label for my input. That's what I'll put it on there as well. So over 20 or 0 to 20 minutes, 8,623 falls between the initial output and the ending output, and we should be good, right? Well, this is where we need to think a little bit deeper, okay? We're going from a situation where we have a plane flying, right? That one is very intuitive to us. Now, we've made this into a function. And now we need to think about what our functions can actually do and how this might not necessarily be enough to say, yes, we're going to achieve 8,623 meters. What I mean here is that sometimes a function can come in and instead of continuing on, let's just say right here at 5,000 meters, let's just say our function jumps up here and then continues on till 10,000. If my function was to jump, would I hit 8,623 meters? No, right? Now, our plane isn't going to jump from 5,000 to whatever this value is. The answer is no, right? Planes can't teleport. It's not going to happen. So because planes can't teleport, it wasn't even within our realm of possibility. But I think we all have seen functions or can think of a function that's going to give us a jump sometimes. Okay, maybe we'll end up with some sort of an asymptote, a hole in our graph. And what if that hole in our graph happens to occur at 8,623 meters? So we need to add a little bit something to be mathematically 100% on this. Okay, and what we need to say is that we don't jump. We don't have an asymptote. We don't have a hole in our function here. What tool do we have to be able to say that we go nice and smooth from 0 minutes to 20 minutes? Well, we can say that our function is continuous. So we can say down here to prove our 8,623 meters is actually achieved, we can say, we called it f of x, so that we can say f of x is, I didn't give myself enough room, I'm going to continuous over that 0 to 20 minutes. And because it's a nice continuous curve and our initial output starts at 0, our ending output is 10,000, we can be assured that we'll hit 8,623 meters. In fact, we can be assured that not only will we hit 8,623 meters, we'll hit every meter between there. Now, this doesn't assure us that we're going to hit this one time and one time only. Okay, it's just going to assure us that we hit the outputs at one point in time. Okay, in fact, 8,623, because we hit a little turbulence up here, it looks like our plane has achieved that height or that output more than one on more than one occasion. 5,000, it looks like our plane only hit that output one time. So this assurance that we're getting here from the intermediate value theorem, which is what we're showing, is that we are just going to hit those values one time. So let's go ahead and take a look down at the IVT thing here. Here's the real formal definition. Okay, I think this is something that you could find in your textbook. Basically, this is saying the same thing. We're continuous over a closed interval, right? 0 to 20 minutes. And now we're going to take a look at our outputs, right? The one thing that this adds that we haven't really talked about is that our initial output and our ending output aren't the same. Okay, that doesn't, intermediate value theorem doesn't work if the outputs are the same. Then it says every value between these two outputs, right? Every value between 0 and 10,000, there will at least exist one value where we get that actual output. All right, so let's go ahead and jump down to number 1. Let's go ahead and see one of these in action, okay? It It says show that g of t takes on the value of 0.499 for some t over the interval from 0 to 1. Now, the first thing that I'm always going to check is I'm going to check to make sure that I have a continuous function. Okay, if I don't have a continuous function over my interval from 0 to 20, okay, or over the interval that they give me, then intermediate value theorem doesn't work, and I can stop working. So the first thing that I'm going to check down here for number 1 is I'm going to see if we're continuous over 0 to 1. Now, we have a fraction for g of t, which means that if our denominator is 0, our function is not going to exist, therefore not being continuous. So I'm going to investigate where we're continuous at by setting t plus 1 equal to 0. So t equaling -1 makes this function not continuous. Now, -1 does not fall in my interval. So I'm in a good situation here, right? I can say that g of t is continuous, but I have to state where it's continuous over, because just saying g of t is continuous in and of itself isn't true, right? We know that it's not continuous at -1 because it makes the denominator 0. So I have to say that g of t is continuous over the interval from 0 to 1. So I've just ensured that my plane is not teleporting up here, right? I'm not going from 5,000 to whatever that value was. All right? Now, let's go ahead and do our outputs, right? Now, I've given the inputs, but I'm not given the outputs for what I'm supposed to find. So I need to find them, which means that I'm going to take my input of 0 and my input of 1 and plug them into my function. So g of 0, 0 over 0 plus 1, which is 0. G of 1, which is 1 over 1 plus 1, or 1/2, or maybe more importantly for us, 0.5, if we're thinking about this in terms of decimals. So what I'm trying to show is that this function goes from 0, or what I'm saying is that our initial output is 0, my ending output is 0.5, okay, that's our 0 to 10,000 from our plane example, and I want to show that I hit 0.499, that's the 8,623, and I want to be able to ensure that I do that. Now, the way that I can show that is by showing that 0.499 does indeed fall between those two outputs. So I'm going to do that in an extended inequality. I'm going to say 0 is less than or equal to 0.499, which is less than or equal to my ending output of 0.5. So g of t is continuous over that interval, right, of inputs, and the output that we want falls between the initial and the ending output. And because that's the case, we can say, therefore, IVT guarantees g of, and I'm just going to say c, equals 0.499 over 0 to 1. All right.